Um, Good afternoon, everyone. Today is sort of not the standard QuMat day, so thanks for showing up. Today we have a talk by Jens Brede. Jens works at the University of Cologne, but Jens got his PhD in the group of Roland in Hamburg, and then he did a postdoc in San Sebastian, where there's also lots of STM activities, and then moved to Cologne, working on quantum materials and primarily also on proximitized topological superconductivity. And we recently sort of reacquainted ourselves a little bit, also in the framework of sort of a collaboration that we would like to start, or that we have started on doing noise measurements on these type of systems. So Jens, thanks for coming. Very much looking forward to your talk.
Thank you very much, Ingmar, and thank you everybody for showing up. Just so that I have an idea, how many of you guys are familiar with STM and how many? So the vast majority, but that's good, so I don't need to explain there. And for the rest, please interrupt me at any time. So if you have questions, I rather end up, halfway through the talk and having answered some questions than going all the way to the end and, have just entertained myself. I should probably also add, as I love STM, when I went to San Sebastian, actually I went to the group in Enrique Ortega, so he's more famous for photo emission, so it's not so far away, but I also got some experience with some other techniques, and anybody who's been to San Sebastian also knows what a beautiful place it is, so there is some upsides to going there. So be that as it may, today I'm going to talk, as Ingmar already said, a little bit about a system that indeed we are collaborating on. One of the samples is already here. And that is a proximitized topological insulator, proximitized by superconductors. And in particular, I want to convince you that you can see not your typical Fermi surface, but your Bogoliubov Fermi surface. I will get a little bit into it, what I mean by this. But before I do this, I should acknowledge that I will not give you the great why are we looking at topological superconductors and why are Majorana the saviors of the Earth and why are we going to build a topological quantum computer. However, I am working in the group of Yuichi Ando, and he is very serious with these efforts of actually realizing a functional topological qubit and actually using this for topological quantum computation. And there's a lot of infrastructure in the group which actually makes these kinds of projects feasible. I am more simple-minded in that sense that I use STM to basically do a very basic characterization of these kind of systems. And then there's also the big MBE group where I might be able to show some data that is related directly to the fields that they have grown. Okay, that being said, another reason why I like being in Yuichi Ando's group is that they are basically a transport group, from the past at least. So their expertise is making devices. And I'm very much interested in, can we do devices plus STM? So the STM community is in a sense a little bit boring because we have this atomic scale precision and we know exactly what we're doing. Whereas you have on the other side the devices where you maybe not exactly know what you're measuring, but that has a benefit that you can be very creative in the experiments that you do. And it's more flexible to do experiments. So I would like to combine these two things and, get a little bit of a new avenue of things that you can play with. However, today I just want to talk about a simple thing, namely these Bogoliubov Fermi surfaces. And there I have to give credit to the people who already reported this. So I hope you're not too disappointed if I tell you there was this very nice science paper from the Chinese group in GIA already in 2021, where they basically demonstrated much of what I'm going to show you throughout this talk. So credit to them. They really observed this for the first time and really did a beautiful work there. There's also some theory from the group in Würzburg, basically, who already explored one of the fundamental physical effects that is then being exploited to realize these Bogoliubov Fermi surfaces. Then there's also this very nice journal club like Hans Benaka with a nice summary of this paper as well. Okay, with that being said, let's have a very, very easy introduction. I feel a little bit embarrassed now I think the audience here, but it never hurts to start very simple. And one of these very, very simple things that still blows my mind is that we have these solid state objects, the 10 to the 20 power of 23 particles in there, right? And then we can make an approximation that we say we disregard that they're interacting with each other. We're completely treating them as a free electron gas. So make the simplest possible approximation. You would even simpler, not in 3D, but in 1D. You can write down our Schrödinger equation directly. Easy enough. You use plane waves just as our solution. we can solve it, and we get our dispersion relation, this famous parabola, where we have here then basically the states and the function of energy. If we then also consider a real object that has a certain length L, then we can also normalize our wave function, and then we end up with this condition down here. If we go one step further and just look what happens if we also apply the momentum operator, then we see there are also eigenfunctions of this particular solution, and by this we can then define a Fermi momentum straightforwardly. Then, if you're only interested in the bulk properties of the system, right, we do the typical trick, we just use periodic boundary conditions. So enforcing periodic boundary conditions basically sets what is our smallest k value that we can get. In other words, we can just count the number of states here, which we can occupy, which is, I have it written right here, that's basically given by the Fermi momentum, and this is the inverse of the volume, and then you can just count the number of states that you can occupy. If you have a Fermi gas, as we are talking about in this situation, we just have this energy value here, which defines the point at which the highest occupied state at zero temperature is placed with an electron. Above this line, all the states are empty, right? So this is our definition for zero energy of the Fermi energy. In one dimension, this has a little funny form what the Fermi surface actually looks like, but it's trivial enough, right? It's just 2 points. So these 2 points that separate the occupied and the unoccupied states in one dimension would be our Fermi surface. If you want to be a little bit more abstract, you would say from your 1D band structure, you get a dimension -1 Fermi surface, which in this case would be the 0D, the 2 points. If you now do the little mental exercise and go to 2 dimensions, so we just rotate this parabola around the origin, right? Instead of having these 2 points, we now have a Fermi surface, a Fermi line, I should say, is probably more precise because it's the edge of the surface, so it's a one-dimensional object from this 2-dimensional K-space. And this is our Fermi surface. Why did I talk about this Fermi surface? Yeah, I said at the beginning, it's amazing that you can do this very simple approximation and that I claim that we can see this. And one way where we can see this is a very famous 2D surface state of copper, Shockley surface state. So super old also in SDM, I think in photo emission it was even measured already in the 70s. But what you can just do, you can take your SDM, and as you all know, I hope, you're primarily measuring the local density of states. Now record the local density of states as a function of energy. You will see this here in the left window. You can get, and here at the middle you have a defect, you can observe scattering, and it's going to be the scattering exactly of this 2-dimensional state. Whereas here on the right, you just see the Fourier transform of this image at the left. So instead of seeing the real space information, you just see the Q space information. And up here you see the energy which is actually given by your bias voltage. So if we now just let this run, and we see, now we have this one defect as if we drop a little stone into the water, you see the waves rippling outwards. And conversely, you could look at the momentum image of it, and you see how this circle expands outwards. If you want to be a little bit more technical about it, we are not looking at the dispersion relation directly, but we're looking at standing waves. So we are looking at the scattering of an incoming and an outgoing Bloch wave, or a superposition of, let's say, 2 Bloch states. Which means in this particular case, this circle is not going to be directly our KF, but for example, 2KF. But be that as it may, disregarding this little technicality, what we're actually measuring is what we just sketched in the super simple picture, right? So we have our dispersion relation that we could follow, and if we cut now here the energy exactly at the Fermi energy, then this image which we get is essentially an image of our Fermi surface. And then here you can also record this local density of states as a function of energy, and you see this more or less step-like increase as you would expect from the simplest textbook density of states in 2 dimensions, right? And in SDM, we typically like to look at it that way, but a little rotation of the axis. Again, you see the onset of the state, and here you see the cut at the Fermi energy, and here we get the full circle. So you can image this Fermi energy. Now we go a little bit ahead in our physics education. We jump to our master's courses. We've learned all about the little problem that Cooper solved. Then we would have
yes, question. So the density of states is flat, right? To the
yes. So this is these things where an experimentalist doesn't even bother because I just have some linear background in my measurement, but essentially it is perfectly flat. So you should imagine it as a step like this. But the reason is that we're not just measuring the density of states of the sample, but we also have some other factors, for example, the density of states at the tip, but the other one that is more important, you have matrix elements that define your tunneling. That gives you typically some sort of background. That's the reason.
De variëteit dus. De variëteit.
Yes, exactly. If you would draw into the WKB picture, it would be the very invariant. Some more questions? Always, please stop me, especially if you have the feeling that I'm telling you something that you don't believe. And be critical with the images as well. Okay, that being said, we jump a little bit ahead, and now instead of thinking the ideal Fermi gas, we just have electrons and no interactions. We turn on some attractive interactions among these electrons. We have solved the Cooper problem. We have learned all about second quantization. We've done the Bogoliubov transformation of our BCS Hamiltonian. And then I hope many of you are familiar with this picture that you end up with, where probably the theorist already says, why are you wasting all this space on the board instead of just plotting this quadrant, which obviously is correct, and the rest is given by symmetry. But the reason that I plotted like this, so you can pictorially, if you're not super familiar with it, just recognize more or less our parabolas like before. So now we know that we are in a superconducting state. So our electrons are paired up. In this particular formula, now we describe the excitations of the ground state as a superposition of electrons and holes. And that's why you basically have the doubling of this parabola. Then if you turn on the interaction between these guys, it's almost like you know it from your band structure in the solid, right? You would draw your parabolas, and then you get the one from the next Brion zone over exactly at the crossing point where you have a degeneracy. When you turn up an interaction, you open band gap. Similar sort of logic, even though completely different physics, also applies here. So you get your opening here of the band gap. So if we now measure the density of states of these quasi-particles, we would measure something like this, right? So we see our more or less constant density of states, and when we see the classical DCS, like 1 over the square root of E divergence of the density of states, and we have a gap here, which is for the moment the most important thing. So if we now want to look at the Fermi surface of our superconductor, what do we expect? Fermi surface is still exactly here in the middle of the gap. So if we now image that with SDM, what would we expect to see? Nothing, because there's a gap, right?
Actually, conceptual question.
Yes.
So in these master classes, theoretical master classes, we also say that the superconductivity stabilizes the whole Fermi surface.
Mm-hmm.
So it doesn't actually exist. How does that square with imaging it? Or you asking?
So what we are imaging, because at the end of the day, we're injecting electrons. So what we can image is how the electrons interact with, let's say, the superconducting condensate. I am neglecting the ground state in this picture, right? Because I'm only talking about the quasi-particle excitations from this concept. And this is essentially what one sees. And if one does the tunneling matrix elements correctly for these type of scenarios, it just comes out due to the fact that the coherence factors and everything, at the end of the day, they cancel out, and you just measure a density of states as if you were measuring a semiconductor, essentially, even though you're really measuring the interactions of electrons with these Bogoliubov quasi-particles. But in terms of the stabilization, I fully agree with you, right? So this is maybe a good point to bring this up. The fact that this is stable is the energy gain of the system, right? You gain energy by condensating in the superconducting ground state. So the fact that you don't have density of states at the Fermi energy is exactly what makes this quote unquote surface stable, which is not really existing in that sense. But yeah, just for the sake of this presentation here, right? The point that I wanted to get is that we expect to see no Fermi surface. And this is just an image of such a scenario. It's no longer this copper surface that I showed you before, but here we take again an image at exactly the Fermi energy, and we see absolutely none of these standing waves. And also here, you just see basically some intensity, but that is technical details because we have finite size for these images. Essentially, we don't see any pattern in the Fourier transform. Whereas if you look slightly above the Fermi energy, so 3 millivolts, so somewhere here, we see these very distinct features. That is clearly the scattering that we see. So in this very naive picture, it's exactly what we expected. So here we see our standing waves due to scattering from the iso energy surfaces. Here our iso energy surfaces gap out, so we don't see anything anymore. And there's some interesting stuff, which I will get to in a second, that happens when we apply magnetic field. But basically, this is just to set the stage.
Yeah, do you actually detect Josephson currents?
You could detect Josephson currents if you wanted to, but you would need then a superconducting tip as well, right?
Yeah,
So
exactly.
this is your.
This is with the normal.
This is all with a normal metal tip, just measured. Again, always please interrupt if you have questions. Great, thanks. With that, the stage finally is set to talk about what I really wanted to talk about, namely these Bogoliubov Fermi surfaces. Just to give you a very, very brief reminder that we now have no longer a free electron gas, so spin degenerate system that we're talking about. We'll be talking about a topological surface state that is being proximitized. So you have all these good things like spin momentum locking, and most importantly for this kind of context, also that the spin degeneracy in the sense is lifted, that basically the copy of this one surface state lives on the other surface. And this is then being proximitized. But you can disregard this for the moment, all the details, and just consider it more or less like the free electron gas before. This is then what a typical film looks like, where one of them also made it to here. So here you see these islets, which are just grown bismuth telluride layers on top of niobium-111, which we deposited on sapphire substrate. I should say that it's just minor technicality. I'll mention it here that this interface is not very nice. So the surface of the niobium is always oxidized. I'm also convinced that there is intermixing and nasty things happening between the tellurium and the bismuth at the interface layers. But we're not too terribly concerned with it because at the end of the day, we are only interested about what happens here on the top surface. And the top surface looks rather nice. And more importantly, it shows very clear signatures also of this topological surface state, as I will show you in a second. This is just an atomic resolution image, so you can see that this image I already aligned for you. So it's actually really this region. The little bump here is this guy, but it's only to make the point, get nice atomic resolution. We see these defects, which are related to bismuth interstitials, but nothing too out of the ordinary. You can already see it probably a little bit here. You see these lines. Yes, please.
Same situation that, like in bismuth selenide, you have selenium vacancies, which makes it naturally endoped. Do you have here similar things with the tellurium vacancies, which makes it naturally endoped?
So the logic is exactly the same. So you would expect that tellurium vacancies will endope the material, whereas you have excess bismuth or bismuth interstitials that would draw a bit more towards the p-type. So the logic is exactly the same as for selenium compounds.
Yeah, and what do you have here in this?
So these that you see here in this particular case, if you look very closely, you also see that the top of it, the atomic lattice is still continuous, and this is the tellurium lattice. So these things are underneath the surface, and by comparison with the theory and what other people have published, I think this is bismuth interstitials.
So it's p-type.
Yeah, you will also see the spectroscopy in a little bit. The film is still terribly n-type, so I can spoiler this already for the next slide. But from the defects, it's leaning a little bit towards p-type. But this is also a peculiarity with SDM, right? It looks like you have lots and lots of defects. But if you would actually do the count here, it's very little. So that is even good. Since you are interested in it, I think I also mentioned that this is a little bit accidental. So you could take a different part of the film and it will look completely different. So there's a very strong correlation between structural defects in the film and accumulation of native defects. And also, so in that sense, it's not a very nice homogeneous system, but you can find very nice and homogeneous areas. Okay. Yeah, then just, like I said, for a moment, we ignore that we have this topological surface state. If we don't, you probably would ask the question, why do we see standing wave patterns at all? But again, if you don't have the question, we just ignore it. And this is the same what we showed you before for the copper surface. So I can again, just record this energy dependence. It looks a little bit different, so you don't see the circle, but these pouches, which has exactly to do with the fact that we are looking here at this topologically protected surface state and not a free electron gas. But the more important part is we clearly see also here the behavior we expect. So something is opening up to the top. If we just plot that a little bit differently, you get basically this picture here, right? So these are basically the cuts from the map before. We can do a little bit of fitting. And if we just linearly extrapolate this as we would expect it for the topological surface state, which has a linear dispersion, we can then also get the Dirac point. This down here is the corresponding large-scale spectroscopy. So this Dirac point here is somewhere here. And now you can see that here's the onset of the valence band, and here the onset from the conduction band, and here's our Fermi energy. So we are extremely n-type, right? So we are deep in the bulk conduction band, and more than 300 million electron volts above the Dirac.
So what would be the total level here then? Because
I mean,
because it's even in the bulk band, so the number would be humongous. It would be in the
so is there
20 probably.
is there a clear reason why it's so endowed?
Can be a reason, probably depends a little bit who you talk to. So one thing I think that is generally accepted is that the interface with the niobium will naturally cause an N-type doping. So pretty much any metal you would put your TI in would cause an effective N-type doping. I personally think it has also a lot to do with that there is nasty things at the interface happening that we don't see, that it's so much. But if I have the time, I will show you that we can counterbalance this somewhat, and we can also get systems which are not so strongly N-type. But yeah, or here the point is just this is not even unique to our system, because here to the right of it, I just plot the spectroscopy for this bismuth telluride grown on niobium diselenide, where you have a better interface, but effectively it's essentially the same argument, the same kind of doping, also very N-type.
And this is with niobium in the superconducting state. This is with niobium in the superconducting.
Yes, it is. Yeah.
Did you check it when you can you go above the superconducting temperature?
Yes, I will show this also in a second, but just to mention, we also can look at this niobium film before we put deposit with the TI, so we have the full characterization from all ends and angles. Yes, okay. So then just, we are in the superconducting. Indeed, we have superconducting proximity effect in the top TI surface. And yeah, this is just a typical average spectrum. Here, this is just a map, basically in spectroscopy grid taken in this area. Whole point here is it looks rather homogeneous. At least for zero field, it looks like rather homogeneous. You have your Fourier speed features, and we have a clear gap. Again, very similar to what was reported already earlier from the Chinese group. Now we look what happens if we apply a magnetic field. Also answer your question. So here 7 Tesla, I stick to that first. This is basically enough to kill superconductivity completely in the niobium film. So for the sake of the argument, you can consider this your normal state Fermi surface. Then if you just look at the which is exactly again this map taken at the Fermi energy, you see here clearly these wavy patterns and structures. So we clearly see standing waves of the Fermi surface. Whereas if we here go to the other side, we barely see anything. Also note the scale. So this is a 10 times enhanced scale over this one. So it's a really, really, really small signal because we don't have a very hard gap here. But let's say for the sake of the argument, we don't see any scattering here.
Yeah, that's a technical question. How do you do the DRDD map at zero bias? So do you, I mean, it's a constant height.
So these are all spectroscopy grids.
Spectroscopy grids, okay.
So spectroscopy grids, for the non-expert, means we just stabilize our tip sample distance at a given height, defined by a set point condition, turn up our feedback loop, and then record different bias voltages. Several, usually very few, because to get this high resolution, it is very time consuming if we do this way, but you can live with that, let's say. It's manageable. Yeah. So the comparison that you have here in energy is basically, this is really inside the gap, whereas here 6 millivolt, it's very close in terms of the dispersion relation that you don't really expect a difference, but it's clearly outside the gap. And here, if you compare just outside the gap, this is a typical thing that we see with SDM. If you look at standing waves or this quasi-particle interference, and we play with a magnetic field, namely nothing changes. The changes that are induced in the electron systems by an external magnetic fields are typically on energy scales which are much smaller than all kinds of broadening things that cause our characteristic standing wave patterns. But if you look here just in the superconducting state, there's clearly, I mean, without playing anything, doing anything to the data, there's clearly a very pronounced difference. So this map here looks very different from the one at 7 Tesla in the normal state. And then the even more interesting case is like half a Tesla applied, and here it's just applied in the y direction. And you see a more or less stripy pattern here, right? Whereas if you have this same field strength applied in the x direction, you see clearly a different pattern. So something, you're imaging something different depending on the field direction which you apply. With respect to
below 4 Kelvin.
This is all measured at a 400 millikelvin. Sorry, I forgot to mention this. So this is all, part of the superconducting condition. Okay, so what is going on? Probably most people when they think superconductivity think zero resistance states, so we can use this to transport current without loss. But probably the better hallmark of superconductivity is that it expels and makes a magnetic field, right? So in other words, when we apply an external magnetic field, screening currents will be on the surface of our superconductor and thereby expel the external magnetic field. And a very, very smart person, Volovik, pointed out quite some time ago that when you have screening currents running, then your superconducting condensate is no longer at rest but in motion. Now, if we excite out of the superconducting condensate, which is in motion, from the perspective of our rest frame in the laboratory, these quasi-particles will essentially be Doppler shifted, right? It's if you were to jump out of the moving bus and you are the person looking from the streets. And if you work that out, then you realize that there's actually a critical velocity, essentially the lambda criterion, right? So when you have super velocity which moves with such a speed that you basically hit the gap edge, the lambda sense, that will be the point where you have for the macroscopic state, microscopic excitations. In other words, you have loss and it starts to break down. Here in this case, it's more graphically the depiction. This is the point basically where parts of the Fermi surface are no longer gapped out. So this is already, when you reach this critical velocity, you overcome basically the superconducting gap for these excited quasi-particles. And that leads to these characteristic banana shapes. Obviously, because now you start to close the gap, it goes back to what you pointed out a bit, you will make the whole state more unstable, right? And therefore, it's no surprise that you have only a very little parameter space to play with before the state completely breaks down. But yeah, then the dispersion relation of the Bogoliubov Fermi is slightly modified. So this is what we had seen before, and we just now have this extra kinetic energy term due to the Doppler shifting. This is a derivative of the dispersion relation of the particular branch that you're looking at, and this is basically the QuMat momentum. And how this QuMat momentum occurred is exactly what I told you before, right? We apply in-plane magnetic fields. We get screening currents to the right angle, so they will be flowing in that direction. And then you can also already, I think, guess how the directionality comes into play, right? So if you were to rotate the field now from the x direction to the y directions, the supercurrents will also flow in another direction, which of course can also translate over to these bananas, or as you see here or here, be rotating by 90 degrees. Okay, with this, we basically have all the ingredients to again look at what we just looked at before. But no magnetic fields, no quote-unquote Fermi surface, nothing to see. We apply a magnetic field, here in this case, in the y direction. So that means, let's say, the right sides of the bananas, the x planes, the parts of the bananas become visible. So in other words, we get standing waves basically in this direction. Here we now apply the magnetic field in the x direction, being a supercurrent in the y direction. Let's say the upper sides of the bananas become visible. Now it's important that we no longer have this perfectly circular Fermi surface, but this little bit more complicated shape. That means we get two other scattering vectors. And in the normal state, again, everything is there.
Yes, because I think I lost you.
Okay.
You lost me. So you're talking about magnetic fields in the x and y direction.
Hmm?
So the supercurrent should generate a counter directed magnetic field. They basically expel the magnetic field. But these are thin films now. So I mean, how much of a supercurrent can you set up in the film thickness direction? It seems
again an excellent question, because I will get to that point in a few slides. So I sort of mix things here, right? Where I pretend I have a superconductor, which is bulk, and then you just have these, very thin layer at the surface of the order of the London penetration depths, where you then have your supercurrents running. But now we have a thin film, so things will change. But this is actually what the Würzburg guys worked out, and actually it will immediately explain the difference between our experiments and what the Chinese guys have seen in a moment.
Well, wait a second, question. Why should you minus help as not the next?
Because I didn't want to cheat anything that's just by chance that was a direction here that was applied there. I will also show, I think on the next slide, it was a plus y direction. Maybe it does by accident, but it was not selected on purpose with that in mind. It's a coincidence here. It's just the direction that was applied for this particular time. Yeah. Okay. It is not as clear as you will see it in some other images. That's why I will not spend too much time. But basically, you have here intensity, and less intensity at these points. Whereas when you then rotate the field by 90 degrees, here you get an enhanced intensity, and this intensity here is reduced. Especially the second statement, you don't really see so clearly, which is something which is a little bit puzzling still to me. But there may be a simple answer to that as well. Be that as it may, as it was pointed out, why did I show minus 500? Here's the plus 500, just for for comparison. This is just a simple experimentalist consistency check. Do we measure something that makes any sense? First of all, these difference images down here, because I normalize it by the sun, you can already see it in these maps up here. They get very low values, so let's just forget about those. So I just throw out these very small values. Don't want to hide anything. It just confuses everything. But now we can just look. So here we have, let's say, y direction, x direction and y direction, and we subtract the two of them, and we see clearly that we have this intensity enhancement here. So red is high intensity, positive values in this color scale. Of course, then I can also subtract from this one, this at minus 500, and then I get the same image more or less, just with the opposite sign as you would expect. Then I can also subtract the plus x and the minus x. Where within that picture there should be no change, and indeed there's mostly no signal visible here, I would argue. And then you also can do the same game, where you're above the gap, where you don't expect any changes. Yes.
Sorry, how did you normalize?
So this just normalized by the sum. So instead of just plotting the difference, a minus b, I divided by a plus b. So there is no deep physical meaning. It's just to play a little bit with the intensities that something shoots to the roof. The main problem being here that you have values very close to zeros, and always looks nasty. But
So before you subtract them.
So it's really just the difference divided by the sum of the two images. So really, this image minus this image minus this image divided by the sum of these two images together. But it looks better actually. So the signals look much stronger if you don't do this normalizing by the sum. But it's also a little bit misleading because small experimental details can cause a real big difference in the signals. That's why I find this a little bit. Okay, yeah, so basically all the consistency checks works out. So it seems like we're measuring something that is at least not an experimental artifact. So the next thing obviously to check reproducibility. This was the one example I just talked about. And you see the maps I just showed you. This is basically this corresponding spectroscopy also. So you see this very clear gap without field. If you apply these indent fields, this gap starts to close, but you clearly still see these peaks, which are in a sense more important, that tell us there's still superconductivity going on in the system. Whereas if you go to these hidden Teslas, it's essentially a flat line as you would expect, and there's no superconductivity involved. So this would be another sample. You see the names up there. It doesn't need to concern you too much. Here you see more clearly what I was alluding at in before. So here, if you apply the field the y direction, you very clearly have these scattering vectors. Whereas if you apply the field with the x direction, you clearly have these scattering vectors, which are less pronounced within the other one. But overall, essentially the same features are happening. Here, the spectroscopy looks even nicer in the sense that you could also clearly see this peak feature, which appears when you close the superconducting gap. And then this would be the data from the sample that we measured for bringing it over here. Again, same story. So if you have in y direction, you clearly have these scattering vectors. Whereas if you apply the field in the x direction, you have these scattering vectors. And spectroscopy, benevolent eye, you see the same features that you see before with some small differences. Okay, reproducibility is good. Then look what the masters did before. So this is the data from the Chinese paper. Not their way of plotting it, just for comparison. I took their data, right? Nowadays, everywhere you have to also publish your data that is accessible. So I just used their data and plotted it with my color scales just to have it more immediately comparable. So if it's not to the lighting, it's not their fault. So you see here now, same pattern, same story. So they also see, in this case, the field has to be applied in the y direction again. So here you have these arcs pronounced, which are the less pronounced here, and whereas these four become more pronounced when you then rotate magnetically. Here, this comes to your question now. The field that they need to apply to get the same kind of effect that we see is 40 millitesla. Whereas let me jump back. Here in this case, it's something like 400 millitesla. In some other terms, it's more like 500 millitesla or 600 millitesla. So clearly we see the same thing, but it's a factor of 10 difference in the field scales. That should make one worry a little bit that maybe there is something we overlooked, or we're looking at something that is not the same. Maybe Zeeman is coming into play and it's not supercurrent. But if we just go back to what we can already learn from what other people have calculated before, we come to this very simple picture. So it's really the exercise is, so maybe I should also mention this. So the supercurrent velocity is essentially given by the vector potential in this particular direction. So The exercise here that they did here in Würzburg is they went to the London gauge. This is the geometry with the field applied in y direction. And you just do a sort of finite size superconductor, and then you just look at the distribution of the vector potential in that scenario. So you just solve essentially the electrostatic equations. And when you do that, you actually end up with this term, which is sort of the key. So that you see you have this tangent hyperbolicus formula here. Meaning in the case of this bulk niobium, the thickness of the superconductor is, let's say, infinite compared to the coherence, the penetration depth. Therefore, this factor is essentially 1. So they get the full force of the effect, because this is indirectly proportional to the vector potential, which is directly proportional to the Doppler shift. Whereas we're in a scenario where our thickness of the superconductor is smaller, or at least similar than the thickness than the London penetration depth of the superconductor. So for niobium, bulk niobium would be about 40 nanometers, which is also our film thickness. But as you go thinner and thinner with the films, the penetration depth also goes up. So probably it's even more unfavorable. But let's say we are in the factor of 1 to 2, that would make this 1/2. That would already bring our field strength that we need to get the same effect basically up by a factor of 2 to 3 or 5. Or if we are more gracious with our estimate of the actual coherence penetration depth, then it even goes up to a factor of 10, which is what we observed in the experiment. So we are still quite confident that indeed the screening currents are the crucial parameter which induces the effect that we see. And it's not, for example, the Zeeman effect. If you're familiar with topological insulators, the shifting that you saw there basically will also end up right with the Zeeman term due to the spin momentum locking of the TI surface. So if you would apply the magnetic field in the one direction, you would shift the surface over in the dicta direction. Okay, so all seems to be nicely consistent. And personally, I'm still super excited with this beast. So that we have now something which is, it's not a Fermi surface, it's a Bogoliubov Fermi surface. So in a sense, we see these the interaction of our tunneling electrons with these quasi-particles excited from the superconducting state. In this particular case, the gapless superconducting state. And by doing simple tricks like changing the direction of the external magnetic field, we can play with the surface. So we really have a very nice handle experimentally to interact with it. And it seems to be incredibly robust. So like it doesn't look always super nice, but we always see this effect. So this is still something which baffles me a little bit, because I would have always expected this state would be super fragile and everything needs to be right. The stars need to align to be able to see it, but we always see this. So it's really, I think there's a lot of things we can do with it. The fact that we need 10 times larger fields, I think, straightforwardly explained by the fact that we're using thin film superconductors and bulk superconductors. Things I did not talk about because I don't have a good explanation so far, and also in a sense it's a detail, but I think it will become an interesting detail. It was not just these 6 banana shapes which go bright and dark there. Especially in the difference images you saw, there was a lot of structure in there. This structure is not at the position that one would expect if all we see is coming from the topological surface state, of the proximitized topological surface state, after it has undergone this transition to the gapless state. There's more going on, but we can still understand. Another thing that should be there, and that we should be able to see, right, if our Cooper pairs have a finite momentum, that means our order parameters, so our gap, should vary in real space. So we should see more or less an oscillation of the order parameter in real space. So this is certainly something to the reason why, at least we haven't seen something clear yet, is the length scale of this oscillation. So then it's very large areas. But also more in terms of theoretical predictions. So this gets very exciting if we now combine having this in-plane field and the gap closing, so to speak, this particular direction, together with Landau quantization. Experimentally speaking, so you first create your vortex lattice, and then you delocalize the vortex lattice in one dimension. And if you do that very close to the chemical potential, then there's apparently a possibility to get something that they termed a Majorana lambda level. So but the dissipation of these excitations in the course are actually not immediately destroying the states, because you have this chirality of the system if you're very close to the Dirac point, which should then protect and stabilize the state. Another thing which I don't have a good answer, but I would love to work out with you guys is, what is the charge of these excitations? You know that for these Bogoliubovs, if they're exactly at the energy of the gap, they're an equal mixture of electron and hole, right? So they have zero charge. But as we deviate slightly from this, they will require finite charge. I'm not really, good on how one could apply shot noise measurements to really get a handle on it, but I feel like there should be a way that one can measure this. And yeah, if one then can really stabilize specific values of this charge, I think I don't need to say much. Now I need to look at the time. I'm already very far ahead. I have another long third part, but I don't want to bore you guys too much.
But we started a few minutes late, so I think we've had a lot of questions. So I would say you can
Press on.
Press on. Okay, excellent. With pleasure. And again, please interrupt me. Questions, always welcome. So now we basically, if you want to be critical about it, we have not done much more than show what the Chinese guys have shown in 2021 that we can also do. We can do it on a thin film, which has some fun implications for other experiments that we can do. I didn't talk about, but essentially we just showed what they've seen already before. Now I will go a little bit beyond this, and then the idea is just what happens now if we take this Bogoliubov Fermi surface and define it, confine it. Yeah, I don't want to go too detailed through the theoretical prediction, but the idea is very simple, right? It's always, if you start with your topological surface tip, where you no longer have spin degeneracy and just spin momentum blocking, you can induce superconductivity in this state. Then you already get this quasi-P-wave area. So you're in this topological superconducting regime. If you have this two-dimensional state and you can confine that state to one dimension, you essentially come down to the equivalent of the Kitaev model, and then you just need to create a boundary and confine the right amount of modes. And if you do that with an uneven number of modes, you always expect to have Majorana boundary states. So that's the very simple logic. And basically the theoretical proposal by Dian Fu is to do just this, and by exploiting either a thin ferromagnetic layer insulator, I should say, ferromagnetic insulator to place on top of the superconductor to exactly induce below this strip then this gapless superconducting state that we just talked about. Or one uses somehow inhomogeneities in this film so that you get effectively regions which have a smaller superconducting gap surrounded by a region with a larger superconducting gap. Then you apply again your intermagnetic field, you get your screening currents, and the gap here will close before it closes in the red region. And you see already from the depiction here, you have a quasi 1D scenario. Sparing all the details, taking advantage that you cannot have normal reflection due to the momentum blocking and then the forbidden back scattering. What it boils down to that basically, if you now confine these gapless states in the y direction, you only get Andreev reflection at the edges. To the larger gap superconductor. Then you only get Andreev reflection back and forth, and then you can just solve the condition for the Andreev reflection, and you will find that you in this channel will always get at least one bound state as a function of the width of this channel, as well as of the magnetic field applied, which are the two parameters which basically determine the phase that the Andreev reflected quasi-particles get. So in other words, by choosing the width here correctly and then just increasing the field, you will always have one Andreev mode which will cross the Fermi energy at a given point. And whenever you have an uneven number crossing, you should be in a topological regime. So what do we need for this? Yeah, positing the ferromagnetic insulator is not our forte, but I mentioned before that these films are not as nice as this one particular area that I showed you in the beginning. So typically you see lots of defects, you structural defects in the film, but more importantly, if you then look closely here at the superconducting gap following this line, it clearly is larger here in this region than it is here in the middle. It's not a huge difference here at zero field, but it's measurable and it's there. So we have already some scenario serendipitously where we have smaller gap regions and larger gap regions.
Any idea where it comes from?
That we have these variations?
Yes.
So the idea is that I shouldn't say this word, but it's not a very good film. So the film is really bad. So here you actually even see that it also coincides with structural imperfections. So it's little islands which grow together and they're no longer perfectly aligned, and then you probably have dislocation lines in between. But It's probably even more complex than this.
In the tensor limit, can it be the film thickness also? Because the proximity effect will depend on the thickness of your film.
Excellent question. You're spoiling, 3 slides ahead where we will show this, but this is actually the smart way then to exploit this exactly so that you have it more by design. It's a little bit coincidental observation. Okay, but more clearly the whole scenario gets when we now apply an infinite magnetic field. So this is now just basically looking here at this end. Now it's no longer plotted so nicely in a different color scale, but I think you can clearly see that down here, the gap closes, whereas up here it stays full. So just to say, when we have the infinite magnetic field applied, we get this scenario where we really enter the gapless scenario only in a very confined space. You can also see this in the quasi-particle interference here. It's all just black and white, but this area here clearly shows quasi-particle interference, but this one doesn't, because it's still gapped out. Okay, with this, I can also mention this. So this goes back to connecting these niobium films before. So from measuring these niobium films, they're very close to the bulk value of the coherence length, 40 nanometers. So the size of these vortices, quote unquote abricosal vortices that we see here, basically gives you the coherence length directly as an image parameter. So we know this is 40 nanometers. So if you look now at this theoretical model that the width of these features where we want to confine something, obviously it should be confined on the characteristic length scale of the system, which is the coherence length. So we would ideally have something which is on the order of the width of the coherence length to get the strongest effect. And the other one, the size is just given by the magnetic field, which we can choose to achieve the proper value. So essentially what we see here, we have something which is in the order of the coherence length, and we can choose a magnetic field in such a way that we go here in the gapless state. So if we believe this prediction, we should be exactly be able, just by varying our magnetic field, to transition from the topologically trivial to the topologically non-trivial case. So from the case where we have 0 bands crossing the Fermi energy to the first mode crossing the Fermi energy, giving us a band inversion, thereby entering the topological receiver. And obviously, if you split that actually with an edge, this is the kind of spectrum you would expect theoretically. If you look at what happened in the experiment, it looks like this. Again, apologies for the plots being not as nice anymore. So this is not playing with the color scale, just barely how it looks. Here you have a gap. You see that it closes. And then you see that there is also some zero bias peak, which remains. And something more happens, which is difficult to see. If you crank up the contrast a little bit more, you see that something opens up here. Then it comes back down again. If you then play even more with the data to visualize it nicer, to take the derivative 2 times with respect to energy, this way you then very clearly see. So you have something as a function of the magnetic field, where the gap closes, you have a zero bias mode, and something seems to happen here where it opens again. Disappearance of the zero bias peak, and then closes again, and then for the fields that we can apply, it remains. So that looks strikingly similar, at least, to the theoretical prediction. But people close to the field are extremely cautious with making any claims that this has to be a Majorana these days, because the really tricky business is how can I distinguish these features that I see from Majorana bound states. Conceptually, there's also some clearer problems. So, I mean, it's good that we see this gap closing and the reopening, and we also see the zero bias conductance peak. But as we pointed out before, we are not really in this regime discussed here in the theoretical proposal where you only have the topological surface state, which is being proximitized. So we clearly have bulk states around. So that might complicate things a lot also in terms of which modes are available and so forth. Another thing is that so high above the Dirac cone here that our topological surface state is no longer perfectly spherical. So we're in a strongly warped regime, which is also the explanation why we can't see quasi-particle interference at all. So there's certainly some things which make us at least pause. Some of these we can tackle. I will run through this very quickly. So this is the expertise of our MBE guys. So by playing basically with the ratio of bismuth and antimony, you can play from a material which is, let's say, natively very N-type with a chemical potential in the bulk conduction end, to the material where you have natively P-type with a chemical potential in the bulk valence band. And if you just play around with the composition, in our case, typically tends to be about 0.7, you get a scenario where your chemical potential lies here in the bulk gap, and also your Dirac point is well exposed. Not explaining much, so what you see here is Landau level spectroscopy. So this particular peak here is marked with 0, is directly a measure of the Dirac. And you can see for this particular ratio, we really have the Dirac point exactly within 5 or so of the Fermi energy. But we can make these films, and we have to take advantage of another thing we've been playing around with. We can cleave these films. So they're ground on sapphire substrates, but you can cleave them off these sapphire substrates. So by that, you can basically invert such a heterostructure. So the film here is grown on sapphire, but we then put a niobium layer on top. We turn the whole thing around, and then we can just cleave off the sapphire. And by that, we then have access again to a nice clean surface and can look at the proximity effect in such a structure. This is what was alluded to a few minutes ago. If we then look, at a particular spot, so we look on this film for a hole that has, during this cleaving process, sometimes you also rip out little parts of the film, and you end up with a certain hole. And this is what you see here. So here, basically, have several terraces. So I think this is more or less the 0 layer or the first layer. This is like 2 layers higher, and so forth. You see the corresponding labels here. And then if you now just look at the superconducting gap, you see exactly as it was predicted, as you make the film thicker and thicker, the induced gap decays. So it gets smaller and smaller. Again, you're not the first to do this. This has been done very nicely on niobium diselenide with this bismuth telluride, and they also see a characteristic decay. The data that we get basically follows what they see before. So it's very well established in terms of numbers, what kind of thickness and what kind of gap you expect. And now we just had to get really lucky. That's this weird thing. So it almost looks like, you were drawing this, but for some weird reason, this particular part of the film exposed this very long wire-like structure, which almost looks like a metal hand down here. And this is even on top of it all, exactly in the side range, so between 5 and 6 nanometers, so where we still have these very strong gaps. So now we really have this almost textbook example that we have the large gap region, the small gap region, and it's a film which is bulk insulated. So we clearly have here the bulk valence band, the bulk conduction band is up here. We have this additional feature here, it's a little bit worrisome, but be it as it may, it's still above the Fermi entity, so it's clearly also about insulated. Now we just play the same game that we played before, and we apply a magnetic field along the wire. And this is then what we measure here in this case. So you have this nicer induced gap to start with. So it's really a hard gap here. But then if you apply the magnetic fields, you need to apply in this case a higher field, which is probably due to the fact that the superconducting film is thinner. We again see that this gap closing, and after it closes, you see the 0 bias peaks remaining here and a gap reopen. So it's very much the same behavior. Yes, please.
So the bismuth telluride layer gets thinner and thinner, and at some point you won't get a surface state anymore.
Correct.
What point?
So it depends a little bit on who you want to believe. So typically experimentalists would put the limit at 3 layers, where you say that the intersurface hybridization is so large that you gap out the surface state. Theoretically, I think in most calculations, it's more like 7 layers where the intersurface hybridization.
But you didn't see any edge modes in that one.
So if you wish, this is an edge mode in the sense that it is a Majorana mode. If we want to be optimistic and call it a Majorana mode. So this fact that after this gap closing here, now we see a feature appearing is exactly this equivalence of the edge mode. It's just here we are in a 1D scenario, right? Because we have this 1D structure, so we get basically these end modes. And they're not dispersing anymore because they are really at 0 modes. So they are the 0 modes and 0 energy bound states, if it is at the end of the day what we hope it is. Okay, with this, I just do the side-by-side comparison. I think my time is also clearly running out. Essentially, we see the same picture in both scenarios. So this is the one I just showed you, which looks cleaner. Again, here, this is just a third derivative to enhance the contrast, to make things a little bit easier. Overall, you have a larger gap. It looks cleaner, which sort of intuitively is appealing because now we have our chemical potential, at least in the bulk band gap, so there should be less unwanted modes around, which would spoil our signal. So it should be closer to the ideal theoretical scenario, and it at least doesn't disagree. Let's put it this way. The downside is, for example, even with our maximum fields that we can apply, we cannot go to the scenario where we would expect the gap to close again. We'll see then the benefit of the zero bias mode, which we did see in this particular case, which most likely is related to the thinner niobium. Yeah, so this just, again, so we're very close to this. And with this, and come into this summary for the second part. And the good news for us, it's very good news in the sense that we at least reproducibly can create this scenario where we at least conceptually, we have created a scenario where we have induced superconductivity in a topological surface state. We confine it to one dimension. We play with a parameter where we expect to isolate a single mode in this channel. And whenever the single mode crosses the Fermi energy, this is accompanied with a zero bias conductivity that we observe in these structures. So that is the good news. The other good news is also that we have rather large induced gaps. So this is actually a little bit surprising to me. Again, I think it has to do with the not greatest interfaces, but yeah, we can discuss. But the clear downside, obviously, is both of these examples I showed you, they're completely coincidental. So in one case, I got very lucky and had this ripped part of the film, which just ended up being exactly like a wire. But it's by no means that I, fabricated the wire and had it exactly at the position I wanted it. In the other case, I just took advantage of an homogeneous film. So this is then where it goes back to what we're also working on. We now want to fabricate these kind of structures really by design. This is one of the examples where Adrian is currently working on. So we're etching basically now these one-dimensional structures. And we hope that we can reproduce it like this. If that really works, then the way is not so far of really using these kind of devices and then handing it over to the very qualified army in Ando Sensei's lab, who can then really use these zero modes and test if they have, the quantities that we expect if they are Majorana zero modes, namely the non-abelian statistics. So braiding experiments. Anything short of braiding, I think these days, nobody will be convinced that what you're measuring is a Majorana, not something else. In our particular case, I think if we can get this stably fabricated, then we also have the tool in Ando's labs to check whether we can do fusion experiments, for example, with these modes. With that, thank you extremely very much for your.
Thank you, Jens, for a nice talk. We've already had quite a few questions, but we have time for a few more. Daniel?
I lost you in the last 5 minutes where you went to this one, a very interesting one-dimensional state. So in my framework, if you peel off, you might have finally some thin, let's say 5, 6, 3 critical layers which will telluride on top of which would be two-dimensional quantum spin Hall insulator, if you believe theory, and then you would find edge states. These edge states could be called topological superconductive edge states, but that I don't see in your one-dimensional thing. Can you explain?
So I'm fully with you. We could probably debate about whether it's the 5 or the 6 layers or the 7 layers, but I'm fully with you. So if I take the 3D TI and I'll really now consider that I've thinned it down to a critical limit, I get hybridization, for example, of top and the bottom surface, and I want to get a quantum spin Hall insulator. Then the theory picture that I use it to compare my data again is no longer the correct one. So they only consider the 1/2 of the topological surface state, so the typical Fouquet model. So they only consider the proximity effect in the topological surface state. And what happens on the other side, it's completely irrelevant for the modeling. So there's just some magic knot that induces superconducting carrion, but it is the isolated 2D surface state in that model. If your picture is indeed correct, then maybe the best answer I could give, we didn't see any clear indications of an edge mode in the system. But I can say that.
But the edge termination is important. If you have steps, you might be fooled by the steps because you need to go from a topological insulator to a non-topological system.
To make the things even worse, so the guys around Alexei, so they grow these vanadium dope systems, so the quantum anomalous insulator. And we also looked at those samples with SDM, and these are perfectly quantized in quantum experiments. So they can do very fancy and nice quantum transport experiments, perfect quantization, rho SX, all perfect. In SDM, we didn't see any states so far. Maybe temperature is still too high, right? This is all this business that let's say the temperature range, most likely due to low puddles, where you can actually observe the quantum anomalous Hall effect is extremely low. So compared to the induced magnetic gaps in these systems, which are tens of milli-electron volts, you typically need to cool down to 40 millikelvin to observe and measure this perfect kind of quantization. If you warm up a little bit, you get breakdowns. So
What the business on that case, the work of Henk and our experimental work shows that the gap, of course, in the two-dimensional quantum panel insulator unhappily is much weaker than the gap of the three-dimensional topological insulator, which may indeed connect to your low temperatures that you need to see something.
good point. Yeah.
So we find gaps still of 10 to 50 milli-electron volt in the DFT theory for business level, maybe smaller for business level.
But to just answer this directly, I think if I were to look at my data under a different perspective, I might also still come to different conclusions. But in that sense, it's not set in stone because there are several aspects which try one-to-one map to this very simple theoretical model that they used to derive this particular scenario.
Other questions? I have one more. So you mentioned about the etching here, these 1D channels. Do you etch the channels into the niobium before you grow the BST on top, and then you hope to see the sort of the effect on top of the BST, or do you etch directly into the BST?
So we combine basically two things. So for me, it's still the more remarkable thing is, so this is done with clean room-based fabrication.
Yeah.
So we really coat this entire BST film and then do the whole fabrication steps in the clean room and then just etch down. I think in this case with argon I etched. It's just, and after that, we put the niobium on and we flip it.
Yeah.
So the surface, which was, in the beginning with respect to the sapphire, is at the end of the day the one we do as the M1.
Yeah.
That's the only reason why we managed to get surfaces that were so suitable with this kind of approach.
Okay.
If you were to etch from the other side or have resist on it and have to remove it, it's
I was
never.
about to say this is
And this, I still have hopes that we get there, but it's not perfect yet.
but still, I mean, the fact that you can still do this and see something is already very nice.
And I didn't show the data, so you can resolve superconductivity also this. The reason that I didn't show much data is because we didn't see what we wanted to see. So maybe that goes in the direction that we have to consider a different scenario for the data.
Okay, thanks. Opportunity for a final question. No? Then let's thank Jens again for a nice talk.